Okay, so I think we're live now. We can start with the session. Okay. Hi everyone, this is Manish Nath from Hex. Yes. Hi everyone, this is Manish Nath from Hex-Star Universe, and I am going to be your host for today's session. Hex-Star Universe is a space research and development-based platform with a vision of making space accessible and affordable to all. We are enabling learning from the top minds around the world. Welcome to the HSU Show, episode 30. So today we have organized a really special session for all of you. Our topic for today's session is Glimpses of Cutting Edge Astrophysics. And today, to enlighten us on this topic, we have none other than Dr. Prajval Shastri here with us. Well, before moving on with today's session, let me know in the comment section, are you guys really excited about this session? Because we are really excited to have Prajval ma'am here with us today. Well, I think, yeah, everyone is really excited. So let us start with the session. So, well, don't forget to screenshot today's session and share your experience about today's session on social media after the session ends. And definitely don't forget to tag Hex-Star Universe and Prajval ma'am. And also, the person with the highest number of likes will be getting a merchandise from our side. Okay, now moving on to today's session. I don't think Prajval ma'am really needs an introduction. Most of us already know who she is. But for the sake of today's session, I will give an introduction. She has been an astrophysicist for nearly 4 decades. She investigates the physics of giant black holes found in centers of distant galaxies using telescope at multiple frequencies based on Earth and in space. She received her PhD from the Tata Institute of Fundamental Research. She attained postdoctoral research positions at the University of Texas at Austin, the University of California at Berkeley, and Harvard Smithsonian Center for Astrophysics. And after that, she was a faculty at the Indian Institute of Astrophysics for Bengaluru for 23 years. She has been a Fulbright Fellow at Stanford University and is currently Emeritus Scientist at the Raman Research Institute, an Adjunct Professor at the International Centre for Radio Astronomy Research, Australia. She is the founder and past chair of the Gender in Physics Working Group of the Indian Physics Association and a member of the Working Group for Gender Equity of the Astronomical Society of India. She is vice chair designate at the Women in Physics Working Group of the International Union of Pure and Applied Physics. She not only published several research publications and popular articles on astrophysics, but also published writings on gender inequity, science, and society. So, without wasting any more time, we would all like to welcome Prajval ma'am for today's session. Thank you, everyone.
Thank you very much. Shall I start? Hi, shall I start? Can you hear me? Can you hear me? Shall I start?
Yes, ma'am, we can hear. We can.
Okay. Okay, so thank you very much, everyone, and it's a real pleasure to be here and have a chance to chat with you. I'm a bit sorry. I'm sorry about the bit of a delay we've had. There was the usual kind of display problems, but we are, I think, ready to go now. So I will give some glimpses of what is contemporary astrophysics, and these would be a very, very biased selection. It's not going to be complete or all-encompassing, but just to give you a glimpse of some of the things which excite astrophysicists today, and certainly I have made my pick, so they are things which excite me, but as I said, it's just to get you more interested and dig deeper and wider into what astrophysics has to offer. To start with, I just wanted to say that there are roughly 4 approaches to astrophysics research. So there are the theoretical predictions that physicists make. The astrophysicists build instrumentation, which most often uses very, very cutting edge technology in order to look at the sky. And then, of course, we look at the sky in order to test our predictions. And then the other approach is to use computer simulations to compare what we see in the sky with what the computer simulations predict. And computer simulations can kind of be key, because sometimes the theoretical predictions are not tractable, and therefore one needs to invoke computers, especially when we are dealing with things in the sky involving very, very large number of objects, very, very large objects, and multiple interactions between them due to both gravity and fluid dynamics and electromagnetic interactions and so on and so forth. So examples of theoretical predictions. So for instance, Giordano Bruno, a very, very, very long time ago, made the prediction that other stars have planets. And we will see what we know about that today. Perhaps you already have had glimpses of that. Einstein, for example, predicted that masses must bend light. And then again, Roger Penrose predicted that collapse to a black hole is inevitable when stuff is beyond a certain mass. And that was a rather rigorous prediction, which was impelled both by theoretical understanding and by some of the observations that people had obtained at the time. So this is a representation of the electromagnetic spectrum, and the human eye is only sensitive to a very small part of it, which we call the visible range. But the frequency of electromagnetic radiation increases to very high values through the ultraviolet and X-rays and gamma rays on the one hand, and decreases to the infrared, microwave, and radio waves on the other hand. And astrophysicists now use the whole electromagnetic spectrum for insights into the cosmos. We also use high energy charged particles that come from the cosmos. We use neutrinos, and we use ripples in the fabric of space-time itself in order to infer the physics of the cosmos. So here are some examples of the instrumentation. Remember, I said there were 4 approaches to astrophysics. So this is the second approach, where we build instrumentation in order to access the cosmos. And these are some examples. So on the top left is the Venubapu Observatory in Tamil Nadu. Here in the middle is the very large array located in New Mexico, in the United States. This is the Keck Observatory in Hawaii. This is the Uti radio telescope, and here is the Giant Meter Wave radio telescope. So all 3 of these are windows into the radio part of the electromagnetic spectrum, whereas this and this are more into the visible and infrared parts of the spectrum. And here is a diagram which shows us shall we say, obstruction caused by the Earth's atmosphere to accessing the sky, which is actually a good thing, because if the atmosphere wasn't there, then that would be harmful to biological creatures. But what that means is that to access certain parts of the electromagnetic spectrum, we have to go outside the atmosphere. So being here on Earth, we can access the visible part, shown here, and the radio part of the electromagnetic spectrum. But to gamma rays and X-rays and so on, the atmosphere is not transparent. And that is what is shown on the y-axis on this plot. And you have frequency going from right to left and wavelength going from left to right. And so infrared, ultraviolet, and X-ray light from the cosmos have to be accessed by telescopes that we put outside of the atmosphere. And these are examples of that. So here's the James Webb Infrared Telescope, which has been making waves ever since it was launched recently. Here is AstroSat, which is an Indian astrophysics satellite launched a few years ago. And then there's the Chandra X-ray Observatory, which has been up there for a while now, which gathers X-ray light from the cosmos. This is a facility that gathers neutrinos from the cosmos, which are also important in order to understand certain physics, as I already said. And finally, the Laser Interferometer Gravitational Wave Observatory, which actually is sensitive to ripples in the space-time, in the fabric of space-time itself. And each of them is an enormous engineering feat. This is something we have to always remember. So these are just some more examples. So one thing that I would like to point out is when we display what we see in the cosmos using, say, gamma rays or radio light or neutrinos or something, the eyes are not, our eyes are not sensitive to it. So how do we actually render them? Right? So this is to explain that. So this is a very famous galaxy called the Sombrero Galaxy, and this is a visible light picture of it. And the way we show it in other frequencies is demonstrated here. So this, for example, is a regular picture of a cat taken in visible light. This is an infrared picture of a cat. But what does it mean to show it like this? Because the eyes are not sensitive to infrared, and you see some colors over here. So what does that mean? So this is a technique that astrophysicists use very commonly nowadays, which is called a false color display technique, where each color is a false color. So it does not represent that color. Instead, it represents the intensity of the light received at whatever frequency. In this case, the infrared. So this is another picture, another false color picture of a cat. And you can see that the colors are different. That is just to show you that the colors are not real. They are just used to represent the intensity of what we are seeing. And so a false color picture doesn't make sense unless it is accompanied by a key like this, which shows you what color represents what intensity. So you see a key here and some numbers here. So here you can see that the whitish color is the highest intensity. And this is an infrared picture. So highest intensity of infrared light, and the very dark purple is the lowest intensity, and so on. And this makes sense, right? Because we know that a cat's nose is cold, so it would emit less infrared. And the cat's eyes and the inside of its ears are warm, so that would emit more infrared light, and its body would be somewhere in between. And this also tells you that colors are arbitrary and the choice of the renderer who's creating this image, right? It is not determined by the cat. And so this is just to show you that. So this renderer has chosen a completely different set of colors to represent the same set of data. So exactly the same thing. And we can deduce that it's the same thing because by just comparing this key at the end, which shows us which color represents what. And this is just another example where you have a human holding a caterpillar, and so the caterpillar is of course colder than both the human hand and the sort of shirt sleeve on the wrist, and that is sort of reflected in this key. So we do the same thing for astrophysical objects. Here is that Sombrero Galaxy again, and this is what might be called a true color image, in the sense that the colors in this image kind of mimic the way the human eye would respond to something like this if we could actually see this galaxy. In reality, the human eye, naked eye, cannot see this galaxy because our eyes are not sharp enough. But if they were sharp enough, this is how we would see it. On the other hand, a false color representation of the same galaxy, the same picture, is shown here in green. So this is a picture in visible light, the same picture, but represented as a false color picture. So here, the intensity of the green light tells you the intensity of the light that is being received. And the same galaxy as seen in X-rays is shown here in blue, and in infrared is shown here at the bottom. And you can see that the three are not looking identical, which is not surprising because the X-ray light is coming from somewhat different phenomena. It's not coming just from stars in the galaxy being hot. It is coming from things that are called X-ray binaries, where you have this star in a binary in a partnership with another star, pulling mass from it, which swirls around this first star and then gets accelerated and heated and thereby emits X-ray light. And so the stars which are bright in X-rays are very different from the stars which are bright in visible light. And in infrared light, you see something even more interesting. So if you notice here in visible light, there is this dark band across the galaxy, this dark strip. And that strip is not because there are no stars there. That strip is because there is a lot of dust there. We know that now from a lot of investigations. And dust tends to absorb the visible light and get then heated itself. So then it gets heated to temperatures which is such that they emit light which peaks in the infrared. And that's exactly what you're seeing here in this picture. So what is seems like a disk with a dark edge, here it looks like a proper ring. And this is the ring of stuff, of dust, which is being heated by various processes in the galaxy. So what looks dark in visible light looks like a ring in infrared light. And this image is sort of all of these things overlaid one on top of the other using a computer display. So that's about false color images, and I hope now you will realize how astrophysicists render their images that are taken at frequencies which the eye is not sensitive to. So this is just to show you the telescope. So this is the Chandra X-ray telescope which has taken this image. This is the Hubble Space Telescope which has taken this image, and of course also this one. They are just two different renderings. And this is the Spitzer telescope which has taken this infrared image. Another thing about astrophysical images and astrophysical data was illustrated, among other people, by this scientist called Grace Hopper, who was one of the pioneer programmers. And she used to give a lot of popular talks, and she used to carry along a 30-centimeter long cable for talks. And the reason she would do that is to demonstrate that light would take 1 nanosecond, that is 1/1000th of a second, to traverse that 30-centimeter cable. This was just because we think of light as traveling instantaneously in our everyday experience, but actually light also takes time to travel. It's just very, very fast. It has a speed of 300,000 kilometers a second. And therefore, although we don't notice it in our everyday happenings on Earth, light actually takes more than a second to reach us from the moon, and more than about 8 minutes to reach us from the sun. And so therefore, we can never figure what is happening in the cosmos immediately. Even from the moon, we can never figure what's happening right now. We can only know what's happened a second ago. Similarly, we can only know what happened about 8 minutes ago from the sun. And so we're always out of date as astrophysicists, which might seem like a bad thing, but actually it is a good thing, because we as astrophysicists one of our hypotheses is that, the universe is kind of uniform. We are not in a specific place. And so, if we want to learn the history where we are, for example, okay, all we need to do is look very far away, because the further away we are looking, the deeper we are looking into time. So we are receiving light from earlier and earlier epochs when we look further and further. So in other words, there is here, then. So we can learn our own history to very, very early times by looking very far away into the cosmos. Another very important technique that astrophysicists use is called spectroscopy, meaning you spread the light that you have as much as is possible through either through mostly spectrographs, but also prisms and so on, in order to split the light such that we can start to see the atomic transitions that happen in these objects. So this is just to illustrate the set of sort of the emission line pattern, if you like, which you have probably seen at some point in your lab experiments when you've dealt with, say, a sodium vapor lamp or something. And so this is just showing the different patterns that gases of different elements would show over and above a sort of a continuous rainbow-like background. And you can see that each element has its characteristic set of lines. So what happens is, if, let us say, you have a so-called hot black body, if you put its light through a prism or a spectrograph, you would get a sort of a rainbow-like thing. Instead, if you saw this light through a cloud of gas, instead of seeing it directly, you would still get that rainbow kind of thing, but you would also get light being absorbed by this cloud of gas at certain characteristic frequencies. And if you were to absorb that cloud of gas directly, instead of seeing black lines, you would actually not see this continuum, this rainbow-like thing, but only see the lines. So this kind of a spectrum, it's technically called an absorption line spectrum, where you have a continuum, a rainbow-like thing, and then dark lines. That is what you see from the sun, for example. So you could even point a CD at a grazing angle at the sun, and you would see its spectrum and these lines. And those are characteristic lines of the content of the sun. So hydrogen, whatever else is there in the sun. Now, the important thing is that while these lines and their positions in the spectrum, meaning at what frequencies they occur, tell us about the composition. That is, you remember this spectrum. So you can see that each element has a certain combination of lines. And so by seeing which combination of lines we see, we can actually infer the composition of the whatever hot gas or star that we're looking at. But there is another very, very important consequence of the fact that we can see these lines from cosmic objects. And that is that just like there is Doppler shift of sound, there is also Doppler shift of light when the source of light is moving. And so let us say we're looking at a star and we're seeing its spectrum, as we call it, the rainbow with these dark lines. Suppose that star is moving towards us, then these lines would all be shifted to higher frequencies, and we call that blue shift. And suppose that is moving away from us, all those lines would be shifted in frequency to lower frequencies, and we call that red shift, because the wavelength becomes longer, or quote unquote redder. And in the case of the blue shift, the wavelength becomes shorter, and so quote unquote bluer. And so from this, we can infer the motion of that gas cloud, which is from which we are measuring these emission lines, which is very, very important, because then that gives us insights into the kinematics and therefore then into the dynamics of what is happening with these gas clouds or stars or whatever. I will now get to something called the angular size. So we have the moon in the sky, and the moon in the sky looks roughly the same size as the sun in the sky. So obviously they're both not the same physical size, but it just so happens that the sun is 400 times larger physically than the moon, but coincidentally is also 400 times further than the moon. So the sun and the moon look roughly the same size, and that size is actually an angle. So it's actually the angle that the moon subtends at our eye. And so we in fact measure it in units of either degrees, minutes and seconds, or radians or something. And this is just to show you that in the sky, those of you who are amateur astronomers have probably seen the Andromeda galaxy, which is one of the closest galaxies to us. And what we see with the naked eye is, or even with an amateur telescope, is just the central part of it. And actually the galaxy is rather big. And in the sky, the angle that it subtends is much larger than the angle that the moon subtends. It's a few degrees across. So relatively speaking, if they were to be side by side in the galaxy, the Andromeda galaxy would be much bigger. So that's just to illustrate to you this idea of angular size of the galaxy. So angular size is the angle that the object subtends at our eye, and it is also used to measure separation of two different objects. So let's say two different stars are separated. The angle that the separation would subtend at our eye would be the angular separation, and it would be measured in angular units or degrees or minutes or whatever. I just want to mention that in astrophysics, for power, we use the power of the sun as the unit, and the power of the sun is roughly 3.9 into 10 to the power 26 watts. And similarly, for units of mass, we use the mass of the sun very often as a unit, and the unit of mass is that many kilograms. So one of the earliest sort of theoretical predictions, I mentioned it before, was by this astronomer called Giordano Bruno, who said that stars other than our suns have their own planets. So he was actually, this was an idea that went completely contrary to the beliefs at the time, and he was actually burnt at the stake for his views. But today, with very, very modern technology, we know that what he predicted is true. There have been many, many planets found around stars, which are like our sun. I think my slides are slightly out of whack. Just one second. Don't think that was the right sequence. Okay, so this is just to show how modern day astrophysicists discover these planets. So we cannot, we don't have telescopes sharp enough to actually image the planets next to their star. There's also the problem that the star is extremely bright and the planet does not have light of its own and just reflects the light of its star and so on. But there is a very interesting way in which planets are discovered, and that is illustrated here. So what you're seeing here is just a diagram which shows a star, and let's say a planet is revolving around it. Now the planet, if the planet's orbit is kind of edge on to our line of sight, then there would be a time when the planet would pass between us and the star. right? And so in a sense, that is called a transit. So when it is passing in front of its host star, the light from the star would be reduced by that tiny bit because the planet is in the way. And this would happen in a very periodic fashion because you expect the planet to revolve around the sun. And what is shown here is the kind of data we would get from such an observation. So here is the light from the star, and it is shown as a function of time as we observe this system. So let's say the light from the star is roughly constant. It may be flickering a little bit, but when the planet comes in front of it, it will reduce by that tiny bit because part of the star will be hidden by this planet. So the light from the star will be obstructed by this planet. And then once the planet is off of the star, as from our point of view, the light from the star will go back to normal. So this needs very, very precise measurements of the amount of light from the star. And this is a method that has been used now for some time, as a result of which about 4,000 stars in our galaxy have been found to have planets, and some of them have multiple planets. And so the number of planets is a few thousand. Skip this. Another very early discovery was made by Galileo about planets, where he discovered that the planet Venus showed phases just like the moon does. Now, as you know, perhaps, Galileo is the first person, as we know it, to turn a telescope skywards. So he didn't invent the telescope, but he turned the telescope skywards, and he made a lot of very, very interesting discoveries. So he, for example, found that Venus had phases. He found that the sun had sunspots, and so on. So these were very, very interesting discoveries. And this is an example of how the scientific method progresses. So I wanted to use this quote from Yashpal, who said that children are born scientists and breathe science at every waking moment. But when science is pictured as done in ivory towers, it destroys the little scientists. So what did he mean when he said children are born scientists and breathe science? It's that to humans, it is very natural to go by the evidence. So a small child, for example, crawls and falls, and a couple of those falls and the experience of those falls teaches it about gravity, right? So, so that is what Yashpal meant here. And it's a very natural tendency for human beings to use the scientific method to understand the world around them. And Yashpal has sort of posited that when scientists sit in ivory towers and do their science, they destroy that sort of natural tendency that is there in little scientists. But I gather that today the audience has many citizen scientists among them. And citizen science is really about breaking ivory towers. So I'm really happy to share whatever I have to share with all of you. Just give me a second. My slides got messed up a little bit. Just one. So here are some examples of telescopes that study the cosmos, and images from these telescopes are most popularly displayed or rendered using the false color technique, which I just mentioned. So why this is really important is illustrated here. Um, So here is a very familiar image to you, the image of Saturn, and this is taken in visible light. And here is an image of Saturn taken in radio light. And remember, I talked about false color picture. So this is a false color picture of Saturn taken in radio light. And you can see that it's roughly similar to what Saturn looks like in visible light. You can see the disk of the planet, and you can see evidence of Saturn's rings here. Now, this is Jupiter. An image of Jupiter taken in visible light. And this is the image of Jupiter in radio light. And you can see that there's almost no resemblance between the two. And we know that this is also Jupiter only because this radio emission comes from exactly the same spot as Jupiter. And the reason this is very different is because it turns out that Jupiter has a very, very strong magnetic field, which accelerates particles, which then emit this other kind of radiation called synchrotron radiation, which we get only when charged particles are accelerated in a magnetic field. And so that light from Jupiter overpowers the radio light that one would normally see, like the way Saturn shows radio light. And so we see this really strange kind of shape to Jupiter in radio light, which actually reflects all these charged particles being accelerated in its magnetic field. So this just tells you that it is this tells you why it's important to look at objects in the cosmos in multiple frequencies, because otherwise there would be physics that we would never perhaps learn. So I already talked about this. Somehow my slides got duplicated. Okay, so this is actually, you will recognize it, the Orion Nebula, and it shows you what really, really sharp imaging can tell us about. So if we look at it with our naked eye, we would just see it as maybe a sort of fuzzy star, but actually it is a stellar nursery. It is a large gas cloud where stars are currently forming. And this is the view from the Hubble Space Telescope of what is happening in Orion. So visible light. But if we go to this, and this is another such example. So this is called the Carina Nebula. And on the left is what you see in visible light. And you see a lot of gas, dust, and stars which are forming. And on the right is the same picture in infrared light. And now this is a false color picture because the eye can't see infrared light. And you can see that you see many, many more stars in infrared light than you would see in visible light, because the dust that goes along with these regions, where a lot of stars are forming, actually obscures the visible light, but infrared light is able to come through because those particles are transparent to it. Sorry. This is the James Webb, not James Webb, but it's a sort of a diagram of the James Webb telescope, which was launched recently, which images the cosmos in the infrared. And it has given us extremely sharp images of the sky, much even better than the Hubble Space Telescope in some instances, not sharper necessarily, but because of the access to the infrared band, one can see these stars, one can penetrate through the dust clouds that exist in regions where there's a lot of stars being formed. And so here you can compare an image of the same piece of sky with the Hubble Space Telescope on the left, and you can see that we see very few stars there, and compare that with the image taken by the James Webb Telescope, and you see many, many more stars in this region, which is forming a lot of stars. And just in passing, I want to mention that these stars are in the foreground. And you can see that they're primarily sort of cross-shaped, whereas the James Webb shows these hexagonal spikes, which are artifacts. But that's because there are these supports for the secondary mirror of the telescope, 3 of them, and that creates these artifacts which have threefold symmetry. So these are foreground stars, and so they don't tell us about the object of interest. But by looking at such images and the artifacts, you can kind of guess at which telescope the image is from, because it reflects the sort of physical structure of the mirrors in the telescope. This is another image from the James Webb Telescope of a very famous object in the sky called the Stephan's Quintet. So there are actually 5 galaxies visible here, 1, 2, 3, 4, and 5. These have come very close and are interacting with each other. It turns out that this galaxy actually is not gravitationally bound to these, but it is proximal to it in the sky. And the James Webb Telescope has been able to do a very, very fine slicing of the light from this galaxy in particular, which we knew hosted a very, very big black hole in its center. And that is what I will explain now. So perhaps you have an idea as to what a black hole is. So just to explain that intuitively, if we're standing on Earth and we throw something, it's going to fall to the ground. We throw it a bit faster, it will go further but still fall to the ground. But there will come a speed at which it will entirely escape the gravitational field of the Earth. And for the Earth, it turns out that that speed is about 11 kilometers. Now, there is this formula which gives the quantitative relationship between the mass of something and the speed at which it needs to be launched in order to completely escape the gravitational field. So if we keep the same mass of the Earth and squeeze it to a much smaller size, then obviously the spot from which we throw these things is much closer, and therefore the escape velocity increases. And so you can imagine squeezing the Earth with the same mass, keeping the same mass, to such a small size that the speed at which something can escape becomes the speed of light, then it means that nothing can escape. And that is what we call a black hole. And so it turns out we need to squeeze the Earth into almost a marble size in order for it to become a black hole, which might seem a little unrealistic, but larger the mass, less of a squeeze it is to get a black hole. So for example, the sun needs to be only squeezed to about 6 kilometers diameter to get a black hole. And if you remember Gargantua from the movie Interstellar, that has a mass of 100 million suns, and therefore squeezing it to a black hole is even less of a squeeze. So Einstein had propounded a new way to understand gravity, where he said this is curved space-time, and then that curvature directs masses as to how they should move. So therefore, light follows the curvature of space-time, and therefore also clocks tick slower, close to masses. And so when Einstein proposed theory, the same year, an astrophysicist called Karl Schwarzschild discovered a solution which popped out of Einstein's equation. And at that time, the interpretation of that was highly questioned and debated. But now we know that that is the same as what we would call a black hole. I will skip these slides because otherwise I won't get to what I want to say. So this is a picture of the Milky Way. Many of you may recognize it. And in the center of the Milky Way, it turns out that that center is marked here by this yellow circle, which is near the tip of the Sagittarius constellation. And that center was imaged in the infrared with a telescope which gave very, very sharp images. And those data were put together into an animation. And these images started to be made in 1995 and are going right up to the present day. So those data are shown here in this picture. These are real data where this is a false color image. So each multicolored splotch is a real star. And there is a cross in the middle to indicate a position, and you will see why. And this these set of images put together show us that these stars are not moving randomly or in straight lines. They are moving in elliptical orbits around a point designated by that cross. And so we can apply Kepler's laws to this, which is what these scientists did. This animation was produced by this physicist called Andrea Ghez, using the data she got from a telescope located in Hawaii. And the application of Kepler's laws tells us that there is a very, very massive dark object at the position of that cross. And given the fact that this yellow, this star which is executing this yellow colored orbit does not collide with it, but actually continues on its way to make an elliptical orbit, shows us that this mass must be much smaller than the distance of closest approach of this star. And so that gives us a mass of 4 million times the mass of the sun for this object there, which has to make it a black hole. So you perhaps know that Andrea Ghez, along with Reinhard Genzel and Roger Penrose, won the Nobel Prize in Physics in 2020 for this work. I should also mention that this black hole that Andrea Ghez and the others found in the center of our Milky Way is a giant black hole, masses of 4 billion times the mass of our sun. But there are smaller black holes which are scattered all over the Milky Way, which are the result of collapse of stars when they exhaust their fuel. And we have about 70 odd such black holes, smaller black holes known, which are a result of these stars finishing their fuel, so to speak. And they are scattered all over the Milky Way and also all over in other galaxies. And it is such black holes that coalesced to give ripples in the space-time itself, which were detected by this telescope called LIGO, which is the Laser Interferometer Gravitational Observatory. And these ripples in the space-time is what LIGO detected through interferometry. And I encourage all of you to look at the video made at the time of the first discovery, which was, and a description given by Gabriela Gonzalez there, which is a very evocative description of this result. So I won't go into details of this. And just to mention that the scientists Ryan Weiss, Barry Barish, and Kip Thorne got the Nobel Prize in 2017 for this discovery. Here is the Stefan's quintet, which I showed you earlier. And this is a rather older picture, this galaxy, this group of galaxies, which are actually gravitationally bound, as I said. And this is the image by the James Webb Telescope of that same group of galaxies. And as I said earlier, this galaxy is actually not gravitationally bound to the others. And James Webb showed a lot of detail from this galaxy, which is what I show here, where we can actually see the emission from different, not just different parts of the galaxy, but also different components of the galaxy. So for example, molecular hydrogen is emitting light which is distributed like this. The atomic hydrogen, it emits light which is distributed like this. And so all of these, as I said before, are false color pictures, and they tell you about the kinematics of the gas within this galaxy, which then is additional information to the information that we get out of just observing the stars. So these are data from the James Webb Telescope, and this is just a very evocative illustration of how this science is for everyone. The data are public. They have tools to analyze the data and look at data and slice the data and these images in different frequencies, like the one I saw before. And so it's an illustration of how science can truly be made as belonging to everyone. So to go back to Einstein's theory, masses bend light, like I said earlier, because masses curve space-time, and light simply follows the curvature in space-time. Now, if you had a black hole, therefore, which is a very high concentration of mass in the cosmos, then the light from the surrounding stars should get bent by the curvature of space-time around in the close vicinity of the black hole. However, that's something very, very difficult to detect, because the kind of contrast you get between the darkness of the black hole itself and the light from the other stars is somewhat less. However, a telescope, which actually is an array of telescopes and not a single telescope, called ALMA, attempted to detect this silhouette of a black hole. So it's an array of telescopes in the sense that these telescopes are located on different continents, not just far apart, but on different continents altogether. And they simultaneously looked at certain objects in the sky, and the data from each telescope was gathered and then put together offline. For this, you need very, very accurate atomic clocks at each telescope, which does the timing at which the photons are arriving from the cosmic object, so that when you then put them offline and put them together, they actually line up exactly, because the atomic clocks can keep very, very accurate time. So one of the first objects they looked at was this galaxy called Messier 87, and this shows the galaxy in visible light, which is the light is mostly coming from stars in the galaxy. And this is what this galaxy looks like in radio light. Now, this is a false color picture, and what it shows is that from the center of this galaxy, which contains a very, very large black hole. This has been known by looking at the dynamics of gas around this black hole. And so this contains a very, very large black hole, and matter that comes close to it swirls around it, gets heated, and then plunges into the black hole. hole. But in the process, it gets heated to such high temperatures that it becomes plasma. So then there are magnetic fields which are generated within this plasma, very large scale magnetic fields, which because of the swirling matter get twisted. And when they get twisted, they kind of have this spring-like action. And so some of that plasma, instead of plunging into the black hole, is launched out in two jets or streams. And those emit a lot of light as well, because they contain magnetic fields and highly energetic particles. And we see that light most intensely at radio frequencies. Not only that, this phenomenon seems to have gone on for a while, perhaps multiple times, and so you see that these streams of plasma have spread the plasma into the intergalactic space around this galaxy. So this is a very, very large volume. Here is the distribution of stars, and this galaxy is located right here in the middle. And you can actually see a very feeble stream coming out, which is also part of that same plasma that is ejected out by this massive black hole. And from the gas dynamics, it had been estimated earlier itself, there is a very, very massive central black hole here of about 6 billion solar masses. And when the telescope that I mentioned here, when this telescope looked at Messier 87, and this was at millimeter frequencies, and this is just to show you that here is the galaxy with the stars, which is placed in the middle here, looking at this portion with very sharp telescopes in visible light, in radio light, and in X-ray light, shows this stream of plasma that is coming out of the central region. And it was hypothesized that it was a black hole, and the mass was calculated to be about 6 billion solar masses. When ALMA telescope looked at this, lo and behold, it saw the silhouette of the black hole. And so this was exactly what was predicted. This is a zooming in of about 1 million times here. And so here, what you see glowing is this matter, this plasma that is swirling around before plunging into the black hole. And the dark area, of course, is the silhouette of the black hole. So this confirmed the earlier calculation that there was a 6 billion solar mass black hole in the center of this galaxy called Messier 87. The same thing was done with the center of our own Milky Way, which is located here. And with the same technique, again, the silhouette of the giant black hole in the center of the Milky Way was found. And remember, there was an earlier result which used stellar dynamics to infer the mass of central black hole. Here now was a confirmation with an entirely different technique, which was interferometry, as I showed you, with these multiple telescopes, imaging it at millimeter wave frequencies. And so these two confirm each other. And that is the power of science. And what is shown here is a computer simulation. So remember I said that there are these different approaches to how we do astrophysics. So this is a computer simulation of what would happen if matter approached a massive black hole like the one seen in the center of our Milky Way or Messier 87. And what it shows you is that this matter will swirl around before plunging in. But because it is a giant black hole and because it curves space-time, like I said before, we see this sort of hat-like shape because the swirling around happens and it glows, but the light from the backside of the black hole, so to speak, which normally would not reach us, is now reaching us because it is curved by the curvature of space-time around the black hole. And so we see this sort of hat-like structure here and this ring-like structure here. And that is what we are seeing over here as well. So this is a very nice coming together of very, very different observational techniques. In this case, the tracking of stars and how they move around that central area. And in this case, looking at the radiation at millimeter frequencies and what is its shape and which area it's coming from, which showed us the silhouette. And here, the computer simulations, which incorporate both the general relativity and the dynamics and the gas and so on to show you what the glowing gas would look like. And they all come together very beautifully. So this is just to show you that. So this was that other galaxy, Messier 87, which showed a silhouette, and this is the central of our Milky Way, which showed a silhouette. So now to make a leap outwards, this is an image of a very small piece of sky, which is about the 10th of the size of the moon in the sky. And this was particularly chosen to be a very, very nondescript part of the sky, where there were no bright objects, no galaxies, no bright stars, no bright nebulae like what I showed earlier. And the Hubble Space Telescope stared at this small piece of sky for about 12 days in 1995 and found 3,000 galaxies in it. Now, this experiment was repeated in a different part of the sky with a better camera that was put on the Hubble Space Telescope. And it was a smaller area, only a 10th of the size of the moon, and found 10,000 galaxies in that area. So except for these couple of things which show artifacts like I described earlier, and so there are 4 ground stars in our own Milky Way. Every dot and smudge here is a galaxy which has 100 billion stars, and therefore it probably has a giant black hole in the center. And then the more recent James Webb Telescope did the same thing for a piece of sky that is 1/20th the size of the moon in the sky, and again thousands of galaxies in it, also the 4 ground stars with the artifacts that remind us that this is from the James Webb Telescope. And as you can see, billions and billions of galaxies. So this means that everywhere there are billions of galaxies. So what are the lessons that we learn from the study of the cosmos for our own place in the universe? One thing that we have learned is that our Earth is very precious. We've studied Mars and Venus with a lot of detail. The surface temperatures of Mars is more than 450 Celsius. The surface temperature of Venus is more than 450 degrees Celsius. Mars, the surface of Mars is equally sort of hostile, the way we look at it. We've discovered many, many planets in the Milky Way. About 4,000 stars are known now to have planets around them, and there are about 5,000 planets which have been discovered. This is just an artist's impression. We don't actually see the planets. As I said earlier, we only look at, we only get the mass of the planet and how far they are from their host star. And so this is an artist's impression of a planetary system similar to the Earth, because it shows these multiple planets around it. People talk about habitable planets, meaning planets which are at such a distance from their host star such that water is able to exist in liquid form on their surface. However, regardless of how many we have found, we know that there is no planet B, because these planets are so far away that there is no question of our packing our bags and trying to go out there and camp on them. So the Earth is all we have. Carl Sagan urged this photograph to be taken by one of the space telescopes, and it shows the Earth as a little blue dot, rather lonely in the cosmos. That's the zoomed in version of that. And so there is no planet B. And so one is reminded of Gandhi's words, who said, the earth is sufficient for everyone's need, but not everyone's greed. And that is something that we need to follow and safeguard. And so this is what has motivated a bunch of astronomers. Oh yeah, I should mention that um, 3 of the leaders who shaped India more than a century ago were all people who were not scientists themselves, but who had clearly adopted scientific thinking as a way of life, meaning looking at the evidence and coming to conclusions based on that evidence, rather than something that is handed down or something that is written in a book or revealed in a book. So, what is that scientific method? Jawaharlal Nehru said it very evocatively. It is the search for truth and new knowledge, the refusal to accept anything without testing or trial. This is the most important thing. And perhaps equally important is the capacity to change previous conclusions in the face of new evidence. And so the reliance on observed fact and not preconceived theory. And this is what motivated a group called Astronomers for Planet Earth to write this open letter, where they said, we astronomers, astrophysicists, and global citizens recognize the urgency of the climate crisis and our impact on it. We also recognize that we have the power to change our current practices. Comprehensive scientific evidence clearly demonstrates that we are living in a climate emergency that calls for urgent action. So this, for example, is something that is a metaphor for what we are doing to our planet. In the name of lighting our own lives, we are wastefully sending light into the cosmos, polluting our skies, and impacting our ability to look at the beautiful cosmos. So I think I'm out of time, so I'll stop there and take questions from you.
Thank you, ma'am, for this wonderful presentation. Now I think we can move on to our Q&A session for today. So viewers, if you have any question, please feel free to ask your questions in the YouTube live chat, and I will read out the questions. So firstly, we have a question from Teja. Whenever I see images of stars from the James Webb Space Telescope Stellar Nursery, I see those white lights at the exact same angle for each star. I just wonder, why is it so?
I actually didn't quite. I got the point about James Webb, but what is it that is confusing you? Would maybe Teja unmute himself and ask, perhaps, or is he on the YouTube channel?
Well, he is on the YouTube chat, so
Okay, would
he's
you
asking.
just read it again?
Yeah, surely. So he's asking
Not
that
the whole question, but about the image. Yeah.
Yes, so I see those white lights at the exact same angle for each star. I just wonder, why is it so?
So I don't know if Teja is referring to the spikes that we see from stars. So these are seen in all sort of visible light images and infrared light images. When you have a very bright source of light. Okay, so he's saying yes, the spikes. And the reason is that whenever you have a visible light telescope or an infrared light telescope, you have this reflecting surface, and then at the focus of the telescope, you have a camera. Or at the focus, you have a secondary mirror, and then you have a hole in the primary mirror, and the secondary mirror directs the light through the hole to the instrumentation at the bottom. So regardless whether you have a camera or a secondary mirror, it can't float up there. So it has to have these supports. And because light behaves like a wave, those supports cause diffraction of the light. And that diffraction happens in a symmetric way. So in other words, if the mirror was supported by a single support, you would see a diffraction pattern because of the bending of light and its wave nature. Those supports will diffract the light to create artifacts. and the shape of those artifacts will depend on the shape of the support. So I think I mentioned that the Hubble Space Telescope shows artifacts which have a different symmetry, and the James Webb Telescope shows the six-way spikes, which is just because of diffraction from the support system. And why do you see it only for stars and not for other objects? You actually, every source of light would create such an artifact, but faint sources of light will create much fainter artifacts. However, stars are very, very concentrated, almost points of light to the James Webb. And the star is not a point, obviously; it's a ball of plasma. But to the James Webb Telescope or the Hubble Telescope, it is a point source, because they do not see the structure of the star; they see it as a point, and so it's a very, very sharp, intense point of light. And so the relative intensity of the light that is scattered to make these artifacts and the star itself is relatively high. So we see the spikes. So they are artifacts. Does that answer your question?
Okay, so next we have a question from Peter Dasgupta. Why did the Big Bang take place?
Oh my goodness. I don't know. Firstly, I'm actually not an expert in the field of the origin of the universe and all of that. But as to why the Big Bang took place, I wouldn't be able to answer. I do somewhat understand things that happened after the Big Bang, but yeah.
Well, thank you, ma'am. And the next question is, can James Webb Space Telescope take the picture of any black hole?
No, because the kind of resolution that is needed is very, very large. So the James Webb Telescope, the sharpness of the images from the James Webb Telescope are, and or even the Hubble Space Telescope, that's just not sufficient to measure this silhouette. So what happens is that if you have, firstly, of course, as I said already, you need high contrast between the light around the black hole and the black hole itself in order to see the silhouette, right? And we got lucky with these two images that I'm now showing you on the screen, which is the central black hole, the giant central black hole in the center of the Milky Way, and the central black hole in the center of Messier 87. Because there is some stuff which is swirling around the black hole, which shines because it's accelerated and heated, and therefore it's shining. And so there is a high contrast between that shining stuff and the darkness due to the black hole. Now, in order to be able to see this kind of a thing, galaxies which have central black holes, so it's virtually impossible to see this. It's impossible to see this from any of those stellar mass black holes which is scattered throughout the Milky Way that I told you about, which, for example, LIGO saw evidence for those stellar mass black holes by seeing the ripples in the space-time that resulted from two such black holes coalescing. Right now, those black holes, they are too small physically, and therefore too small in the sky in order for us to have any hope of seeing them, seeing their silhouette. The hope we have is with these giant black holes that are in the centers of galaxies. And so in the center of the Milky Way, as I said, there's a 4 million solar mass black hole. In the center of Messier 87, there's a billion solar mass black hole. Now, the larger the black hole, the larger the mass of the black hole, the larger the size of the black hole. We saw that earlier, right? But the angular size depends on how far it is. So even if you have a very, very large black hole, a billion solar mass black hole, if it is too far away from us, then its angular size will be not large enough for us to be able to see the silhouette. So it turns out that the Milky Way central black hole and the Messier 87 central black hole are two which are in that sweet spot. So the Milky Way central black hole is 4 million times the mass of the sun, and therefore it is relatively close to us, right? It's in our own Milky Way. So it's 26,000 light years away. So therefore, it is able to give us a silhouette that is just detectable using the telescopes like the kind I described to you. That is the ALMA telescope. The next possible one is Messier 87. It is much, much further than our Milky Way. So if it had the same sized black hole as our Milky Way, we wouldn't be able to image its silhouette. But it has a much, much heavier black hole. So it's several billion solar masses. So therefore, it's also, the black hole is also bigger in size, and therefore that silhouette was also visible to this telescope. But there aren't too many other galaxies whose silhouette is discernible with the current telescopes.
Okay, so next we have a question from Shubhankar Rana. Can we measure the distance of black holes from Earth? If so, then how? If no light escapes from it?
Yeah, so that's a good question. So first of all, we don't even see black holes if they are just kind of floating around in space, right? There's no way to see them because there's no light coming from them. The only way we can see black holes is either that there is either the stars, there are stars which are swarming around it, like the result I showed for the central black hole in the Milky Way, so that we can measure how fast the stars are moving and then apply sort of Kepler's laws to infer the mass of the central black hole. So that is one way, and that way is possible only for the Milky Way central black hole, because we cannot actually resolve stars for other galaxies. In the case of other galaxies, which are further away, where you can't actually resolve the stars, however, the stars still swarm around, and we can look at signatures of the Doppler motion of the stars in their spectra. So from how much those spectral lines broaden, we can infer what is the spread in their speeds, and from the spread in their speeds, if that spread is very, very large in a very, very small central part, then we can infer that there is a black hole. The other way is through this silhouette technique. So you need one of these techniques in order to actually determine the mass of the black hole. Sorry, can you repeat the question? I'm not sure I fully answered the question. Can you repeat the question again?
Yes, ma'am. So the question was, can we measure the distance of black holes from Earth?
Oh yes, the distance, correct. So the distance, to measure the distance, you need other techniques. So for example, in the case of the Milky Way, or in the case of the Messier 87, we measure the distance not of the black hole itself, but of the galaxy as a whole, using the stars in the galaxy. And the stars in the galaxy make imprints on spectra, as I described earlier. And so from the Doppler shift of the lines, we can infer the speed. The other thing is that there is the universe is expanding. I'm sure all of you know that the universe is expanding, and therefore space-time is stretching, and therefore the light from distant galaxies will be stretched by the time it gets to us. And so when you have these spectral emission lines, which are due to the atoms or the ions in these galaxies, those frequencies of the emission lines are very, very definite. They are determined by quantum physics and they can be measured in the lab. And so if we can identify a set of lines in a distant galaxy, let us say we can identify that this is the hydrogen line, H alpha line, hydrogen alpha line, hydrogen beta line, and so on, the Balmer lines or such lines, whose frequencies we know exactly from the laboratory. Then we can measure the shift, and from the shift, we can measure how much the universe has, how much the space-time has stretched between us and that galaxy, and that stretching is determined by how far they are from us, and so therefore we get a handle on how far they are. Now, once we determine how far that galaxy is, we know how far this central black hole is. So that is the way to determine it. So we have to use indirect ways. If we just had an isolated black hole, we would not, first of all, see it. And even if it had some swirling material around it, we would see it, but even then we would determine its distance from that swirling material rather than from the black hole itself. Is that clear, or did you have more questions?
I think it is clear, but yeah. So next question is from Pravesh Garg. He's asking how we are able to measure the mass of the black hole. For example, TON 168.
TON 168. I don't remember what that is. Can you
I'm so sorry.
describe a little
TON
bit?
618.
Yeah, can you describe what that is? What object is that? I don't immediately recall. I could look it up, I suppose. 1 second.
Pravesh, it would be really great if you can clarify it in the chat.
Okay, so this is a quasar. All right. So, okay. So, what was the question again?
Yes, ma'am. So the question was, how are we able to measure the mass of the black hole?
Okay. So, you remember what I showed you about the black hole at the center of the Milky Way and the Andrea-Ghez result, which got the Nobel Prize and so forth. So they looked at how the stars were moving, right? And so if you have a mass, just like our solar system, we have the sun's mass, and the sun's mass gravitationally drives all the planets in certain orbits. And there is a relationship between the mass and how far each planet is, and with what speed it is moving around in its orbit. So if we had any two of those numbers, we could determine the third. Right, and so that was how the mass of the central black hole of our Milky Way was measured, by looking at the kinematics, as we call them, looking at how the stars in its very close vicinity are moving. So from the speed of the stars and from how far the stars are from that central point, we could determine the mass by the application of Kepler's laws. Now, for galaxies which are further away than our Milky Way, we don't have images which are sharp enough for us to see the stars individually as they move around the central black hole. However, stars are like our sun, so they have these Fraunhofer lines, like the sun does, like the spectra I showed you, because of the elements in the photosphere of the star. And when you have a lot of stars in the central part of the galaxy, we will see the signatures of these elements from each star, the Fraunhofer lines, if you like, from each star, all kind of blended together. But you would still see the lines. The lines would have a much wider width, much larger width compared to the Fraunhofer lines from our sun, because it's not just one star, but many stars, and each of these stars has some motion towards us or away from us. So all of those blend together to give you a wide dark line. Now you can imagine that a star which is moving very fast will have a large speed in our line of sight towards us or away from us. Whereas a star which is not moving very fast will perhaps have less of a speed towards us, away from us. Or if the star is moving in the plane of the sky, even if it is moving very fast, it will not result in a speed in our line of sight. So the speed in our line of sight is what will shift the frequencies of these atomic lines. And so when you have many of these stars, each of them you imagine has these Fraunhofer lines. And there are so many stars, but we are not able to, we don't have sharp enough images to separate those stars. They will all contribute to the line. And so the line will acquire a certain width, which is purely because of different stars contributing to that same line and having different velocities, different speeds in our line of sight, either towards or away. So in other words, from the width of the line, we know the spread in the velocity. So we may not know, we may not be able to apply the Kepler's formula to individual stars, saying this star is moving at this speed and is at this distance from the center. So therefore the mass of that central thing must be so much. That we cannot do, which is what is done in the Milky Way. However, the spread of the line, the Fraunhofer lines, if you like, gives us a spread in the speeds. And so if stars that are moving in the center have such a large spread in speed, that implies a very large mass for whatever is driving. So you still need sharp images because you see the stars in a galaxy are moving in the gravitational field, which is due to the gravitational field of each of those stars put together. So there is this cumulative gravitational field in which the stars are moving, and they have typical velocities of 200 kilometers a second or 300 kilometers a second. However, if there is a central black hole and we are looking at the stars very close to that black hole, those stars will get accelerated to much higher speeds, because it's not the overall gravitational field due to all the stars in the galaxy, but primarily the gravitational field of the central giant black hole which is driving them. So therefore, they will have much larger velocities. They will give rise to a much larger spread in those Fraunhofer lines, and thereby we can measure what is the mass of the black hole. Was that clear, or is there any other question related to that before we go to the next question?
Well, I think it is clear for now. And so, ma'am, should we take any more questions? If you are comfortable, we can go on. Or
yeah, sure. If there are questions, let's take them.
Okay, ma'am. So next we have a question from Ekamakar Singh. His question is, how do the scientists intend to use neutrinos to study the cosmos?
That answer is a very long answer, because there's a lot of things you can do with neutrinos, and I'm actually not a neutrino expert, so I'm not quite the right person to ask this question. But energetic phenomena give rise to neutrinos, just like they do give rise to electromagnetic radiation. And therefore for example, when stars explode, you get neutrinos from that explosion, which can add a lot to our understanding of how these processes occur. So what scientists intend to do is, understand these processes better, because neutrinos can give you insights which which are kind of hidden if you just looked at the electromagnetic radiation from energetic phenomena. But I'm not the expert on that. Are stellar black holes gravitationally bound to supermassive black holes? Not particularly, no. So stellar black holes are created when a star which is undergoing nuclear fusion exhausts all its nuclear fuel, and so nuclear fusion stops. So there is nothing to hold up the large mass of the star, and so it collapses due to its own gravity. And if the mass of the star is larger than a few times the mass of our sun, then it collapses into a black hole. So this can happen anywhere in the galaxy. So the stellar mass black holes are distributed all over both our Milky Way as well as other galaxies. And with the Gravitational Wave Observatory, many coalescing phenomena have been seen of black holes in other galaxies. So these have come together, and so they are distributed. They don't have to be near the center at all. They could be anywhere in the galaxy. However, of course, nothing stops particularly a stellar mass black hole from coming to the center. So through either encountering another galaxy, which then disrupts all its stellar orbits and so on, or some such, or maybe coalescence of smaller black holes into bigger black holes. Near the black hole, it might sort of find its way into the neighborhood of the central giant black hole. Then it would get gravitationally bound by that. It would swirl around, it would get disrupted, and eventually all that material would land up inside the central black hole. But there's no particular link between stellar black holes and the supermassive black holes. What would happen if antimatter would fall in black hole instead of matter? Good question, but you need to sort of, that's not my area of expertise. So you need to ask a sort of general relativist that question, I think. I don't want to give you the wrong answer. What is the mechanism of a relativistic jet formation? Does it come from the accretion disk of the black hole? So the accretion disk is a necessary condition for a relativistic jet to form. We still don't know all the details of how relativistic jets form. However, what simulations tell us is that if you have a giant black hole, well, not necessarily giant black hole, actually. There are jets from stellar mass black holes as well, and there are examples where they have relativistic speeds as well. So if you have a black hole and matter chances upon it and then lands up swirling around it and plunging into it, then some of that matter is seen to produce these relativistic jets. So relativistic jets means that the matter is launched at relativistic speeds, and so the most popular mechanism is something called the Blandford's-Nayak mechanism, which makes use of the fact that the magnetic fields thread the accretion, this matter that is swirling around, which is called the accretion disk, and computer simulations tell us that if you take a black hole and if you put material around it and allow that material to swirl, and if you put in magnetohydrodynamic physics, which means you look at what happens to fluids, magnetized fluids, plasma in magnetic fields, and if you incorporate general relativistic physics in there, then it is possible to generate, it is possible to prevent, in a sense, some of that material from plunging into the black hole and instead getting launched as relativistic jets, twin jets. So it does not come from the black hole. Whatever goes into the black hole goes in, and then it doesn't come out. So the material that is squirted out as relativistic jets is material that is swirling around the black hole, and most of it plunges into the black hole. Some of it is launched outward in these twin jet forms. If black hole attracts everything, how does it radiate Hawking radiation? Yeah, that's a good question. Hawking proposed this radiation. It's never been actually detected. Again, that physics it's a combination of quantum physics and what happens around a black hole with the space-time effects and everything. And again, that's not my area of expertise. So you have to ask a general relativist that question. For my purposes, I know that large mass black holes emit Hawking radiation very, 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 very slowly. Very, very tiny black holes are predicted to emit Hawking radiation. So it sort of goes inversely as the mass. And so from very small black holes, you would expect Hawking radiation, but the only black holes we have evidence for, the smallest of them are stellar mass black holes. So a few times the mass of our sun, and the Hawking radiation would be extremely feeble from such black holes. Why all galaxies have a supermassive black hole at their center? Very good question. I don't think we know the answer, really. So there are many explanations for how these supermassive black holes form. So originally it was thought that they form from the coalescence of stellar mass black holes. So in the beginning of the universe, when the gas first started to form stars, the metallicity of the gas was very low, meaning to say that the gas was mostly hydrogen, helium, and so on. So very, very massive stars can form. A couple hundred solar mass stars can form, and also the universe was more compact. So it was hypothesized that these stars would have chance encounters with each other at the end of their when they're at the end of their life, so to speak, meaning when their nuclear fuel is exhausted, which happens very quickly if the star is more massive. So then these chance encounters would result in the two dead stars coalescing. That way mass would build up and result in the supermassive black hole that we see today. However, there is a problem with this idea because we've been able to see supermassive black holes at earlier and earlier times in the universe, and very, very massive ones at that, even 10 billion times the mass of our sun. So then if it is only through this mechanism of the first stars collapsing into black holes when nuclear fusion is exhausted and then coalescing to form these central black holes, there's simply not enough time to do that, to make these very, very massive black holes at very early times in the universe's life. So then there were two ideas. One is that very, very large gas clouds could collapse not into stars, but into giant black hole seeds of masses of, say, a few thousand times the mass of our sun. And then those would then have chance encounters with other such black holes, and we become bigger and bigger and build up into billion solar mass black holes. So this is one idea. The other idea, which I'm not quite competent to explain, is the idea of primordial black holes as being the seeds for these giant black holes. that we see today. No primordial. Primordial means that they formed very early, very, very early in the life of the universe, and they became seeds around which mass accreted and plunged in, and the black holes grow. So again, I'm not the expert to explain about these primordial black holes, but the point is that primordial black holes per se have not been discovered yet. So this is still a matter of debate as to how these central black holes build up their mass. I mean, we know they build up their mass over the life of the universe by coalescing with other black holes and so on, but we don't know quite how it happened in the very early times, the very beginning. Are neutrinos the key to the secrets of the cosmos? If yes, then how do they contribute to astronomy and how are they detected? Wow, that's a new, completely new area. I already said that I'm not a neutrino astrophysics expert, but I don't know if one can say whether neutrinos are the key to the secrets of the cosmos, but it is true that they tell us physics that electromagnetic radiation alone cannot tell us. And so it is important to try and detect neutrinos from different physical phenomena in the cosmos. How they are detected, I think the best way for you to learn that is, rather than me explaining, it is best if you look at the website of these neutrino observatories. They have very, very good explanations as to how they're detected. We know that every galaxy has supermassive black hole at the center. Where do irregular galaxies have a black hole? Is there a specific place or something like that? And how different are they from normal galaxies? Irregular galaxies are presumably galaxies that are still are yet to stabilize, and therefore they don't have the sort of spiral shape or the swarming shape that elliptical galaxies have. So they would be expected to have somewhat smaller black holes, maybe a tenth of a million, so like 10,000 solar mass black holes. They're different from normal galaxies in how their stars behave. There's much more. First of all, they haven't stabilized into these very nice looking structures. The stars are formed in a lot of different clumps. The stars do tend to be young stars and so on. So these are some of the differences between them and normal galaxies.
Well, thank you, ma'am. I think we don't have any other questions from our chat, so I think we can end our Q&A session for today. But it was really great to see that everyone was participating so actively in the chat and asking so many different and great questions. But before ending, firstly, I would like to thank you, Prajval ma'am, for giving us your time and for this wonderful presentation and sharing so many great informations and enriching us with his knowledge and also answering all our questions. I guess all our viewers have been greatly helped from this session. Secondly, I would like to thank Teja Begari for helping us in organizing this session. And lastly, I would like to thank all our viewers for attending the session and participating so actively, asking questions, and making this session a successful one. And lastly, don't forget to share your experience about this session on the social media, and don't forget to tag us. And also remember that the person with highest number of likes will be receiving a merchandise from our site. So with that, I think we can end our live session here for today. Thank you everyone for attending the session, and also thank you, ma'am.
Okay, thank you.